And today's lesson is on writing chemical equations and counting atoms too. Today we'll be practicing counting atoms in chemical equations with coefficients. And so the coefficients tell us how many of each molecule is present in the reaction. If no coefficient is in front of the chemical formula for that molecule, then there is only one of that molecule. And we'll start today by reviewing a couple of slides from the interactive PhET simulation that was at the end of yesterday's presentation. If you haven't had a chance to go there yet, I strongly encourage you to do so. And the link will be provided to you in the Google Classroom post from yesterday. And it's kind of fun. You can definitely teach yourself a bit more about how chemical equations work. So this was the chemical equation for making ammonia. And it states that for every nitrogen gas molecule, we need 3 hydrogen gas molecules to react in order to yield 2 ammonia molecules. So this coefficient is kind of like a ratio, and the subscript is telling us how many atoms of that element are in the molecule. So it's kind of like this. The subscript and atoms go together. So if there's 2 atoms of nitrogen, the subscript is telling us that, and the coefficient is telling us how many of that nitrogen gas molecule there are. So in this case, there's only 1. And as I mentioned yesterday, we don't normally write a 1 in front of a molecule as a coefficient, but this simulation does. And then, so 1 nitrogen gas molecule reacts with 3 hydrogen gas molecules to yield 2 ammonia molecules. And then let's look at this visually here. So we have 1 atom of nitrogen, 2 atoms of nitrogen, and that creates nitrogen gas, and that's what the molecule looks like. And then here we actually have 6 hydrogen atoms, but because every 2 atoms bonds together to form a molecule of hydrogen gas, we have 3 molecules of hydrogen gas, and the number tells us that. And then it goes through a chemical reaction and yields 2 complete molecules of ammonia. And if we had extra molecules of nitrogen gas or hydrogen gas, they would be represented over here as leftovers. So let's look at the combustion reaction. And this one was a bit more challenging. And I asked you a question in the Google form about how many molecules of oxygen gas were required in order to react with 1 methane gas to create a chemical reaction. And you can see that here in the chemical equation, or you can see it here in the simulation box visually. The correct answer was 2, excuse me. But this is a combustion reaction. So you can imagine that this yield arrow is actually a flame, right? And so as the methane gas from like a Bunsen burner, or if it was trapped in a container of some kind, as you release it into another container, or sometimes they'll use soapy water and blow these gas bubbles into soapy water, the person can scoop up the methane gas and ignite it with some sort of ignition source. And it's going to yield, just like burning a candle, it's going to yield carbon dioxide gas and water vapor. The most important thing for you to take away from writing a chemical equation is that it represents the chemical reaction. Your reactants are going to be on the left. That yield arrow is a one-way street, so you're not going back to your reactants once you've created products, and your products are on the right. And the plus symbol stands for reacts with. And lastly, with this new introduction of the vocabulary word coefficient, the coefficient tells us how many molecules there are. Now, if there's more than 1 atom of an element in that molecule, then that coefficient is going to work like the distributive property. And essentially, the 1 is going to multiply times the C or times the H. In this case, this is a better example. If this were in parentheses, you would know, I apologize for my parentheses not looking like parentheses, you would know that the 2 multiplies against everything that's in that parentheses. So maybe the CH4 would be a better example. Let's pretend that I have 2 molecules of CH4, and I'm going to go ahead and write that in parentheses so we can pretend like we're using the distributive property to multiply against everything that's inside of it. So how many atoms of carbon do we have? 2, that's correct. And how many atoms of hydrogen do we have? 2 times 4 is 8. All right, and then because of the law of conservation of mass, we would expect to find the same number of atoms on the left-hand side as we would on the right, because a chemical equation accounts for all of the atoms that are present in your reactants being present in your products. Okay, let's do a couple practice problems. You're going to be writing in your science notebook on page C14, and you can title the page Chemical Equations Practice. And this is the first sentence you're going to write. It says the total number of atoms for each element in the reactant is always found in the products. If you need to pause, now go ahead, but I'm going to keep moving. This is what your finished page will look like for page C14 in your science notebook. And we're basically doing 2 practice problems where you're going to count the number of atoms in the reactants and compare against the number of atoms in the products and make sure they are the same. All right, I'm going to go into present mode. So try and do this on your own. And I have done this and will provide the answer in just a moment here. But you're going to write anything that's in a black font. So I'm going to read the first sentence. It says, count the number of atoms of each element in the reactants and products. You don't need to write down the word problem or the word chemical equation, but essentially this Fe stands for iron plus 2 molecules of hydrochloric acid, H, capital C, lowercase l, yields iron chloride and hydrogen gas. Now, do I expect that any of you are going to make iron chloride or hydrogen gas in a lab sometime soon? No, but we do need to know how chemical equations work. And it's really important that you write everything in the correct size font, because as we know, a coefficient is full size and the subscript is smaller or a reduced sub size of your full size font. So please write very clearly, and then let's do the next step, which is to count the number of atoms in each element in the reactants. So we'll start with the reactants. How many atoms of iron do we have? Go ahead and write your answer here on your page. How many atoms of hydrogen do we have? Now, we would pretend that there are some parentheses here, and we're going to multiply that 2 against all of the atoms in this molecule. So we actually have 2 hydrogen atoms and 2 chlorine atoms. All right, so your numbers should say 1, 2, 2. Let's go over here to our yields. To our products, and we're going to count the number of iron atoms that we have, chlorine atoms that we have, and hydrogen atoms that we have. So iron's pretty easy. We can clearly see that there's 1 here in this molecule of iron chloride. And then there should be 2 chlorine atoms, right? The subscript tells us that there's 2 atoms bonded together in this molecule. How about hydrogen gas? There's 2 atoms of hydrogen gas. And are those the same numbers we wrote over here? 1, 2, and 2? Okay, good. So that means that we haven't lost any mass, and this means that the chemical equation took place. The chemical equation is written correctly, and a chemical reaction took place. Let's move on to the next practice problem. It says, now try this one. So here's where you do need to write down the chemical name for each one of these molecules. So we have potassium nitrate, plus carbonic acid. Does that potassium nitrate look familiar to anyone else? You'll be surprised to know that it's found in toothpaste, fertilizers, and also in rocket fuel. Potassium nitrate is a compound that is very useful. It has a number of different uses. Apparently, when you mix potassium and nitrogen together and oxygen, it's a very useful compound. And who knows, it may have some uses that we haven't found out about yet. I'm optimistic that some of you will become scientists who apply chemistry to the world around you. And then carbonic acid is basically acid rain or carbonated water. So those are our reactants, and they yield potassium carbonate and nitric acid. So K2CO3 reacts with 2HNO3. So I'm going to draw in some parentheses very carefully here. To help myself count these, and hopefully that's helpful for you. So we're just counting the atoms here. So if you're doing the distributive property, you're going to multiply the 2 times the K, the 2 times the N, and the 2 times the O3. So go ahead and start writing your reactants down here, and I'm going to do the same. So I'm looking at, oh, and be careful because there's oxygen here too. So if you're totaling up all of the atoms, you need to make sure you include these. So for potassium, I have 2. For nitrogen, I have 2. Oxygen is tricky because I have 2 times 3 is 6. And then there's another 3. So I've taken care of my K, taken care of my N. 6 and 3 is 9. Oh boy, I promise that's the number 9. There we go. 2, 9. And hydrogen, it looks like I have 2. Carbon, I have 1. Now let's see if that's the same over here on our reactant. I'm sorry, on our products, excuse me. All right, first off, I am looking at potassium. So it looks like I have K with a subscript of 2. That means I have 2 atoms of potassium. Nitrogen's over here, and there's a coefficient. So I actually have 2 atoms of nitrogen. Hopefully everyone sees that. Oxygen, we should have 9, right? So 2 times 3 over here, that means we have 6 atoms of oxygen here, plus O3 here, that's 9, so that's right. 2 hydrogen atoms, the coefficient says 2, so 2 times H is 2H, or 2 hydrogen atoms. And then it looks like, again, there's just 1 carbon atom. All right, hopefully you got the same. And if you did not, hopefully you're able to see how we counted those atoms. But if not, there is a Google form today that allows you to practice counting atoms. This is a difficult concept for some students, and myself included when I was your age. This was a difficult concept for me to understand. Just know that practice makes perfect. So some of the easier molecules are easier to visually see how to count the number of atoms in each one of these equations. If you have questions, please reach out to me or your instructor, and I hope you have a nice day.